So hello everyone, I'm Norman Wildberger. We're here at the University of New South Wales and this is a course on differential geometry. So we're taking a little bit of a different tack to the subject in this course, and in particular we're emphasizing the usefulness of Lagrange's purely algebraic approach to calculus. And today we're going to push that further and extend calculus in quite, I think, an important way, using this very simple-minded algebraic approach. So the ordinary calculus usually concerns functions of one variable. We have y equals f of x, where f is a function, and we're talking about derivatives and second derivatives and so on and so forth. That's the differential calculus as it's usually presented in a first-year course. Then occasionally we end up also having to deal with curves in the plane which are not of this relatively simple kind. These are curves that are given by joint functions or joint polynomials of x and y. So we might have a curve that looks like, or maybe has branches, something like this, that's given not in this form, but rather in the more general form, p of xy equals 0. Okay. So natural question is, how do we do calculus on such a curve? Well, the ordinary calculus course answers it to a certain extent. For example, you might look at the simple example of the unit circle. So x squared plus y squared equals 1. That's an example of a very important curve that's not given initially as y equals something. But we still might want to calculate its derivatives or second derivatives, tangent lines, and so on. So how do we do that? Well, one approach is to try to convert it into this form by solving for y. In this case, we can do that. We can solve for y equals square root of 1 minus x squared. Okay, there's a plus or minus there, corresponding really to the two branches, that one there and that one there. It is a little bit more complicated, though, because we have to introduce this square root function, which strictly speaking is actually quite a problematic thing to pin down precisely because it involves real numbers. We're going outside the rational number framework. And actually to define the square root of a number is really an infinite process that goes on forever and ever. So it's definitely an increase in complexity going from the polynomials to this kind of function. Okay, but nevertheless, one can do that. One can then try to differentiate these things, but one has to keep in mind that there are these two different branches of the function. However, for a more complicated curve, for example, probably the second most famous curve in terms of analysis is the Bernoulli's lemniscate, which we've already talked about, and I'll remind you that its equation is x squared plus y squared squared equals 2x squared minus y squared. Okay, so it's a little bit more complicated now to talk about solving for y, or if you have a higher degree curve, it may be completely impossible to solve for y as a function of x. So this kind of approach doesn't work. And then usually the approach is, well, we're going to do implicit differentiation. So another route is to take a curve like this and to implicitly differentiate it. So Newton or Euler would have said, well, we're just taking the differentials. So in ancient times, in the 17th and 18th century, people would have said, okay, we're going to take the differential of this. So take the differential 2x dx is the differential of that. The differential of this is 2y dy. And then the differential of this is 0. And then we can solve for dx dy. So dx dy, or maybe dy dx, it doesn't matter which one. Let's do dy dx, it's more familiar. Then dy dx, if we solve for that just algebraically, bring this to the other side, divide by dx, we would get minus x over y. All right, so that would be one possible approach. And implicit differentiation is really similar to that. But then what happens if you want to compute higher derivatives? Okay, there's a relation here. What happens if you want to compute third or fourth or fifth derivatives? And what happens if the function or the curve is much more complicated? It becomes highly non-trivial to apply calculus to these more general situations. In fact, that's usually the reason why you don't deal with these general curves so much in a calculus course, even though you would rather like to, because there's all kinds of beautiful curves that have nice equations that you should study in calculus. All right, so today I'm going to outline how Lagrange's algebraic approach almost immediately extends to this more general situation and gives us a very powerful approach to talking about the calculus of more general curves. Okay? And you'll see that it's really pretty well exactly the same story that we've been talking about in the last few lectures. So let me motivate that. So we're going to talk about Lagrange's algebraic approach to this differential calculus for curves. So the crucial understanding comes about by looking at a curve that passes through the origin. So let's consider a special case. Let's first consider a curve of the form P of x, y equals 0 passing through the origin. So it's going to go through here. So P is going to be for us a polynomial. So this polynomial is going to look like what? Well, if we start with the lowest degree terms, the constant term is going to have to be 0 because we're assuming that it goes through 0, 0. So there's no constant term, and then there's a linear term. Oh, let's make an example up. So say 2x plus 3y, that might be the linear terms. And then we can expect some quadratic terms, perhaps 4x squared minus 7xy plus 3y squared. And then we can expect perhaps some cubic terms, perhaps like 5x cubed minus 2x squared y plus xy squared minus y cubed. And we can keep going to whatever degree we like. Okay, so Lagrange's key understanding, or going back to Euler and really to Newton, is if you want to understand this curve, and let's draw it, so we don't know what it looks like, but we definitely know it goes through that point there. And who knows what it does. Okay, so if we want to understand this curve near the origin, the strategy is simplicity itself. We're just going to adopt the same strategy we've been doing in the last few lectures. The first approximation is that the thing is just 0. That's just the point that it goes through. The second approximation is just going to be what we get when we ignore all the terms except for the linear terms. All right? So the 0th approximation to P at the 0, 0 is just 0, the value. Okay, the first approximation to P at 0 is what we might call T1 up here. So the first approximation, we'll put the point here, 0, 0, and there's the curve that we're taking the approximation of, and that is going to be just the linear part of this. So 2x plus 3y equals 0. Maybe I'll draw it like this, okay? I won't say equal. This curve is given by the equation, we just ignore all the higher terms and set everything equal to 0 because that's the curve. The curve is P of xy equals 0. So if we set everything to 0 and then ignore all the quadratic and higher terms, we get the linear equation 2x plus 3y, which of course is the tangent line to this curve at this point. There's the tangent line. T sub 1 of P at the origin. Okay, the next approximation, the second approximation, well, we can give that a name. Let's call it T2 for degree 2. Still going to be at the origin of P. And that's going to be obtained by taking all the terms up to degree 2 and setting that equal to 0. That's going to be given by the equation 2x plus 3y plus 4x squared minus 7xy plus 3y squared equals 0. That's, of course, the equation of a conic because it's of degree 2. And so we don't know exactly what kind of conic it is unless we examine it more closely. What would it actually be in this case? So here, to find out what kind of conic it actually would be, we would have to look at the quadratic terms, make ourselves a little matrix, 4, 3, and minus 7 over 2, minus 7 over 2. That would be the 2 by 2 symmetric matrix that represents the top part of that expression. And then the crucial thing about this is what is its determinant. So the determinant here would be, what is it? Be 12 minus 7 squared over 4. What's that, 49 over 4? 48 over 4? Is that minus 1/4? Okay, I didn't know it would end up being so close. It's just a little bit negative. What does that mean? It means that the conic is actually a hyperbola. It's passing through here, and it's a hyperbola. Okay, so, well, maybe it would be something like this. That would be one branch, and who knows where the other branch might be. Of course, this is not actually a picture of that curve. This is just some generic picture. Okay, so this would be our second tangent curve, which is a conic. All right, and then the third approximation, well, we just keep on going. The third approximation would be T3, 0, 0 of P, and then that would be all of the terms up to here, 2x plus 3y, plus I won't write them all down, all the way up to minus y cubed equals 0. And that would be some kind of cubic curve. But it's a cubic curve of not the kind y equals f of x. It's a general cubic curve. It's a cubic curve with all possible mixed terms involving x and y up to degree 3. So it could look quite, I don't know, there's lots of possibilities. Maybe it would look like this, and maybe there's a blob here or something. That might be the cubic curve, perhaps. And there's no reason why we could stop here. We could talk about the fourth degree approximation and so on and so forth. So that's really the differential calculus from Lagrange's point of view. It's completely algebraic. What it really amounts to is writing out the object so that we're looking at the point 0, 0. When we're looking at things at the point 0, 0, there's no constant term. And then we just strip off first degree terms or second degree terms or third degree terms, set it equal to 0, and we get one of the Taylor approximations. Okay, so it's very simple in some way. It's also very powerful. All right, so what do we do with a more general curve, not one that's already passing through the origin? So more generally, suppose we have a curve P of x, y equals 0, and suppose it passes through, suppose this curve passes through a point RS somewhere in the plane. That means that P of RS actually equals 0. Okay, I'm going to diagrammatically illustrate this with this curve here. Let's suppose that's the curve that we're talking about, just for the sake of argument. And that the point that we're interested in is this point right here. That's the point RS, and it's on the curve. Now we want to talk about what does the differential calculus tell us about the nature of this curve near that point. All right, so to analyze P near this point, let's give this point a name. Let's call it, say, A. To analyze P near A, what are we going to do? Well, we could talk about it in steps. So step 1 is we're going to translate P so that A is sent to the origin, because we want to apply the previous analysis. In other words, I want to translate everything so that I have the corresponding point here, and the whole curve has been translated. So maybe something like this. Okay. So we're translating. Essentially, we're translating by minus A. Okay, so what's the equation of this curve? If this curve has equation P of xy equals 0, what's the equation of this curve? Let's call it Q of xy equals 0. And what actually is that? Well, that's just what we get when we take P of x plus r, y plus s. The effect of replacing x with x plus r and y with y plus s is to translate the curve by the vector minus rs. And that's why that's the familiar thing that we've been doing all along in this algebraic approach. We have to now evaluate P of x plus r, y plus s. So step 2 is write out P of x plus r, y plus s in powers of x and y. Just like here. So a times x plus b times y plus c x squared plus d xy plus e y squared, and so on, whatever it takes. We know there's going to be no constant term because we've arranged that this thing is 0. If you plug in x and y equals 0, then you get P of rs, which we know is 0. So there's definitely no constant term here. All right, step 3. Take whatever approximation you're interested in, exactly like we did over here. Now the situation is exactly the same as what we started with. So if you want to, you can take the tangent line, or you can take the tangent conic, or you can take the tangent cubic, whichever one you're interested in. So step 3, take the kth tangent, let's say, by peeling off, by truncating, that's the critical word, by truncating this to degree k and set to 0. So for example, suppose we were interested in a tangent, a conic, because that's what we're mostly going to be interested in. So that might be the tangent conic at this stage. This would be the tangent conic at 0, 0 of this polynomial q. But that's not the tangent conic to this thing. That's the tangent conic down here. Now we still want the tangent conic up here. Well, what we have to do is we have to reverse the translation step that we did earlier and translate it now back to where it started. So step 4, take this kth tangent, take the kth tangent to what we're really calling Q, to Q at 0, 0, and translate by not minus A, translate by A to get the kth tangent curve T sub k at the point A of the original P. How do we do that translation? Well, that translation is just the opposite of what we did over here. Instead of replacing x with x plus r, we have to replace x with x minus r and y with y minus s. So to do this, we need to replace x and y with x minus r and y minus s. And then what you will end up with is the tangent conic, or whatever tangent curve you're interested in, to the original curve at the original point. So finally here we get the tangent, the kth tangent, in this case the second one, but in general the kth tangent, at the point A of the original curve. All right, so this is a very exciting program because now it allows us to think much more generally about things. So the case, the familiar case when you're dealing with a function y equals f of x is just the special case when you're dealing with a curve of the form y minus p of x equals 0, or y minus f of x equals 0. So a special case, the case that we considered earlier when we were looking at some curve y equals f of x at some point r, we can think of that just really what's happening now is the point actually on the curve is the point r comma f of r. And the polynomial that we're talking about is y minus f of x, or perhaps f of x minus y, depending on what you like. So we're talking really about that polynomial at the point r f of r. In that case, if you compute the tangent line or tangent conic or tangent cubic in this new way, you're going to get the same thing that you did in the previous story. You either get a tangent line or the usual tangent conic or tangent cubic or whatever. So this is a more general situation. Okay, so I'm going to show you how it goes in a particular example, but I'm not going to go through all the algebra because it's not that interesting, and I've already gone through that kind of thing quite a lot already in the last few lectures. So the example I want to look at is the lemniscate of Bernoulli. All right, so that's the one we already talked about. Looks like this. And there's 1 and minus 1. And the equation is x squared plus y squared squared equals 2 x squared minus y squared. Okay, if we wanted to write it as a polynomial, we should probably bring everything to one side. So we could write it as x squared plus y squared squared minus 2x squared minus y squared. All right, what are we going to do now? Then we're going to compute p of x plus, we're going to choose a point first, I suppose we should say. So we'll suppose that we have some point on the lemniscate. And that point is r and s. So r and s actually satisfy this equation. Okay, so algebraically what we're doing when we do that first step of translating is we're just evaluating p of x plus r, y plus s. So you have to plug x plus r and y plus s in here and expand it all out. Okay, I'm going to write down what we get when we do that. So the terms will be 4r squared plus s squared minus 1 times x plus 4s r squared plus s squared plus 1 times y plus 2 times 3r squared plus s squared minus 1 times x squared plus 8rs times xy plus 2 times r squared plus 3s squared plus 1 times y squared plus cubic terms 4rx cubed plus 4s x squared y plus 4rxy squared plus 4sy cubed. And then the quartic terms, x to the fourth plus 2x squared y squared plus y to the fourth. All right, so to get the tangent line, what we want to do is we want to take the linear terms and then translate the linear terms as just these two terms. That's going to be a line through the origin. Then we have to translate that back to, instead of being at the origin, to over here. And so we can just sort of write off, see what it is that we're going to get. The tangent line is going to be T1 at the point, let's call it A. Our curve is P. So it's going to be a 4r squared plus s squared minus 1. And we have to translate back. So x minus r plus 4s r squared plus s squared minus plus 1 times y minus s equals 0. Equals 0, and that's going to be the equation of this tangent line right here. T sub 1 at the point A of P. To get the tangent conic, well, we have to take the linear and the quadratic term, so this entire first row, that's going to be the tangent conic to the translated curve when the RS point has been translated to the origin. Now we're just going to take that and translate it back to RS by replacing the x's and y's with x minus r and y minus s. So we can do that. So it's going to have equation 4r times r squared plus s squared minus 1 times x minus r plus 4s r squared plus s squared plus 1 y minus s plus 2 3r squared plus s squared minus 1 times x minus r squared plus 8rs times x minus r times y minus s, and plus 2r squared plus 3s squared plus 1 times y minus s squared. Yeah?
Does this not work at the origin?
Meaning?
Like, because it intersects itself, trying to get a tangent line. Like, I just tried it at the origin, if you put r and s equal to 0, you just get, for the tangent line, you just get 0 and 0.
That's right. So that's a very good question. What would happen if we did all of this at this point here? It works for every point. Okay. What would happen if r and s was actually equal to 0? We can see it from here that these two terms here would be 0. So the equation of the tangent line would be 0x plus 0y equals 0. And that's not really an equation of a line. So we are not actually getting a tangent line at 0, 0. I'll talk a little bit more about this. Very, very good question, an important question. So there are some points where special things are going to happen, but you're just not going to necessarily pick up these things in the standard form. But nevertheless, the tangent conic will still exist. Okay, so we have this expression for the tangent conic. Of course, we could simplify it, because we could expand x minus r squared out and so on and collect all terms. And I've done that, and you'll be pleased to know that, of course, we should all set this equal to 0, right? The actual tangent conic is what you get when you take all of this and set it equal to 0. Okay, so if you expand all this out and simplify, you get r times r squared plus s squared minus 1 times x plus s times r squared plus s squared plus 1 times y minus r squared minus s squared equals 0. Oh, so maybe I could write it like this. Sorry, that's the tangent line. Okay, that's the equation of the tangent line. So, sorry. That's a simplification of this thing. That's the tangent line. And the tangent conic, this thing here, when you simplify it, I can maybe go here. The tangent conic will read. All right, so here now it's correct. It's a quadratic in x and y with coefficients which are polynomials in r and s. Okay, so you're all going to be wondering, well, what do these tangent conics look like? And the answer is pretty interesting. So the tangent lines, of course, are just the usual things that geometrically we're familiar with. The tangent conics are more different. Okay, so there's some special point at root 5 on 4. So somewhere here there's a root 5 on 4. Okay. And something special happens at those points. So these 4 points and the corresponding ones on this side, they have tangent conics which are parabolas. Okay, maybe I'll try to. So it looks something like this. So at this point here, the tangent conic is something like this, and it's a parabola. parabola at the point root 5 on 4 and root 3 on 4. Now, there'll be those of you who say, wait a minute, Norman, don't you dislike square roots? And you're absolutely right, I do dislike square roots. So how should we interpret this? So I interpret this in an approximate fashion, as an applied mathematician would or an engineer would. That if you compute a rational number that's pretty close to square root of 5, and compute this tangent conic, it's going to be pretty close to being a parabola. It's an approximate statement. That's the reality of what you get when you're working with square roots. But for those of you who like to believe, you can say, no, there's a real number here, and it doesn't matter if our computers can't calculate it. We can still believe in it. In which case, it's a perfect parabola sitting there. Okay, so there's, of course, parabolas at these points here as well. What about some other points? Well, if we move a little bit in this direction here, let's say somewhere over here, then it turns out that the curves are hyperbolas. The tangent conic is a hyperbola at such a point. And if we go a little bit further out, further up, say, where's my blue one? Something like this. Then we get that's supposed to be an ellipse. A tangent conic that looks like an ellipse. Yeah.
Were they not disjoint?
They were, no, they were only disjoint when we were talking about cubics. And the cubics were only of the form y equals f of x, not these more general cubic curves. So here we see that definitely the tangent conics are not disjoint. When we're talking about conics, yeah. That's right, that's exactly right. So that's what I want to mention now. So the place where the nature of the conic is going to change is where the discriminant, or where the determinant of the quadratic form is 0. Okay? So what we're really talking about is these top three terms here, x squared, xy, and y squared. And it's when this times this minus 4 times this equals 0 that we get, that's like a discriminant equals 0. That's when the determinant is equal to 0, and we get the parabola. So if I look at, note that 4rs squared minus 4 times the other two things, 3r squared plus s squared minus 1 times r squared plus 3s squared plus 1. This thing here turns out to be 4 times minus 8r squared plus 8s squared plus 1. So this is 0. This is 0 precisely when r squared minus s squared equals 1/8. R squared minus s squared equals 1/8 is then the curve that sort of separates the hyperbolic from the elliptic tangent conics. And it's a hyperbola that looks like something like this. Okay, so there's r squared minus s squared equals 1/8 for the point RS in question. Okay, this thing here has a name. This is called the discriminant conic. And there's a remarkable, beautiful fact about these, which I'd like to give you as a problem. So problem, show that the lemniscate and the discriminant conic are inverses with respect to the origin. I'll tell you what that means. So it means that if you take a line through the origin and you see where it meets the discriminant conic, and you also see where it meets the lemniscate. So let's say this point is L for lemniscate, and this point is D for discriminant conic, and this point is O for the origin. Then the statement is that the quadrants between O and L times the quadrants between O and D is constant. Q means quadrants, which is square of distance. Of course, it's also true for distances if you don't mind taking square roots, but we do mind taking square roots, so we're not going to do that. So this is what we're saying here is that these two curves are inverses with respect to a certain circle centered at the origin. Okay, so there's a lot of consequences of this point of view. All right, so suddenly now we can take a polynomial curve, an algebraic curve, and we can talk not just about the tangent line, which is old hat, but about tangent conics. And in particular, for example, this natural question, when is the tangent conic an ellipse? When is it a hyperbola? When is it a parabola? That's going to separate a general algebraic curve into various sections. Moreover, what we're going to be mostly concerned with in this course is not actually curves, but surfaces. And the whole story just translates verbatim to surfaces, really. So this all generalizes in the most natural way to surfaces algebraic in three-dimensional space. So we're talking about surfaces of the kind P of x, y, z equals 0, where P is a polynomial of x, y, and z, which includes as a special case the case z equals f of x, y, which is sort of a familiar surface as a graph. Okay, so you can just write down any polynomial in x, y, and z, x squared y plus x, y, z plus z to the fifth equals 0. That's going to be some surface in three-dimensional space. And to analyze that surface, well, who knows what it looks like? I'll just draw it like this. It won't be like this, but let's just say. Okay. So it's some surface in space. To analyze that surface, we would pick a point on it, say R, S, and T. And to analyze it, at that point, we would just go through exactly the same motions that we've been doing, but with X's and R's paired, Y's and S's and Z's and T's paired. And exactly the same process would then yield not just the tangent plane, that would be the first order terms, but then the second order terms, the quadratic ones, would give us not a tangent conic, but a tangent quadric. A quadric in three-dimensional space is a curve of degree 2. Okay, so there's going to be a tangent plane. Yes, that's the degree 1 part. That's going to look like ax plus by plus cz equals d, something like that. But there's also going to be a tangent quadratic. Oh, who knows what that'll look like? It might be a hyperboloid of revolution, for example. That's an example of a quadratic. So the tangent line, that's the tangent plane. This would be the tangent quadratic. Okay, that would have an equation something like, 3x plus y minus z plus 2x squared plus 3xy plus 4xz plus yz plus z squared equals 5. Something like that. Something of degree 2. Okay, so this is rather daunting because now it seems pretty clear that in order to understand this differential geometry of curves, in the plane we first of all have to understand conics. But we understand conics reasonably well. But we'll see that we can understand conics a little bit better. Okay? And then we have to have an eye on the three-dimensional situation of understanding quadrics. If you write down an equation like this, what are you getting? What are the possibilities? What's it telling you about the original surface? So we're going to have to make a little detour into studying a little bit about conics and quadrics, very classical 19th century stuff. And our point of view is going to be that of projective geometry. So as a kind of homework, please watch the math history video, and I don't know what the number is, that's on projective geometry. Okay, so we're going to try to understand conics and quadrics from a projective point of view. This turns out to be very important with graphics and computer programming these days. So it's going to give us some important new tools under our tool belt to understand curves and surfaces. So we'll see you next time.